This video serves as a quick reminder about basic term structure instruments, both linear and nonlinear. We will introduce fixed coupon bonds, forward rate agreements, floating rate notes and swaps, and then go on to interest rate options such as caps and floors and swaptions. Let's start with fixed coupon bonds. If you recall, a fixed coupon bond, denoted BTT, is specified by a number of future coupon dates, and these dates are denoted T1 up to Tn. Here typically the length of the interval between payments Ti and Ti minus 1 is more or less constant, although there are day count conventions to take care of, but we will not concern ourselves with these. Such a bond will have a coupon rate, as well as a principal or nominal or face value capital F. Usually we will set capital F equal to 1. Such a bond pays at each coupon date Ti a coupon F times C times delta I, as well as the full principal at the maturity time Tn. Such a stream of payments is easy to synthesize using zero coupon bonds, and thus by the law of one price, the value of a fixed coupon bond is given by this expression here. Let's now consider forward rate agreements. A forward rate agreement, or FRA, is an agreement at time little t to lend or borrow money at an agreed rate capital K for the future period from t to t plus delta t. Now, at time capital T, it is possible to lend or borrow at the then prevailing spot rate, LT t plus delta t, and so the payoff of the FRA is simply the spot rate minus the contract rate K multiplied by delta t. And this payoff is received at time t plus delta t. However, the payment from the spot investment, i.e. LT t plus delta t times delta t, will only be known at time capital T, which is in the future. Nevertheless, we can lock it in as follows at the earlier time little t. Let LT t plus delta t denote the simple or LIBOR spot rate over the interval from t to t plus delta t. Thus we have a timeline as shown with little t, then capital T, and then capital T plus delta t, and we have the prevailing spot rate LT t plus delta t over the period from capital T to t plus delta t. Our question is, what is the time little t value of a payment LT t plus delta t times delta t at the time t plus delta t? Recall that the then prevailing spot rate is actually stochastic and therefore will not be known until time capital T. Consider now the following trading strategy. At time little t, we long a T bond and we short a T plus delta T bond. In that case, the value of that portfolio is simply the difference of the values of the two bonds. So we have a net cash outflow of PTT and a net cash inflow of PTT plus delta T. Now at time capital T, the T bond that we own will pay us an amount of 1 unit of currency. We take that unit of currency and we immediately invest it at the then prevailing spot rate. So 1 comes in and 1 goes out, leading to a net cash flow of 0 at time capital T. At time t plus delta t, we will have to redeem the t plus delta t bond that we are short. In other words, we will have to pay 1. However, our investment made at time capital T will yield an income of 1 plus L times delta t. And thus the net cash flow at time t plus delta t is simply the difference, i.e. L times delta t. So by buying a T bond and shorting a T plus delta T bond, I can be guaranteed the LIBOR spot rate times delta T at time T plus delta T. And hence the value of that spot payment is equal to the difference of the two bonds. Now recall that the simple or LIBOR forward rate at time little t for the period from capital T to T plus delta T is the expression shown here. Rearranging, we get the following very natural looking expression for the value of LIBOR spot at t plus delta t, namely the discounted LIBOR forward rate times delta t. We therefore have two expressions for the time t value of a contract which pays the LIBOR spot times delta t at time t plus delta t. On the one hand, it's a difference in prices of two zero coupon bonds, and on the other hand, it's the discounted LIBOR forward rate times delta t. The value of a FRA with an agreed contract rate of capital K and a payoff of L minus K times delta t at time t plus delta t is therefore simply the discounted value of the difference between the forward rate and the contract rate times delta t. The FRA rate is by definition the value of K which sets the value of the forward rate agreement to 0. And as we can see, the FRA rate agrees with the LIBOR forward rate. Now the FRA is the most basic linear interest rate derivative, and other linear interest rate derivatives can often be seen as portfolios of FRAs, for example swap contracts, as we shall see. In practice, FRAs often make payments in advance rather than in arrears. The value of the LIBOR spot rate is known at time t, and we can therefore simply discount it from time t plus delta t to time t. Next, we look at floating rate notes. A floating rate note, or FRN, pays a coupon which is not fixed, but which is linked to a reference rate which is reset every period. Typically, the coupon is LIBOR, possibly plus a spread. Such a contract is specified by a number of future dates, from t0 up to tn, where the coupons are paid at times t1 up to time tn. Typically, the time interval between coupon payments is constant, modulo day count conventions. It has a coupon which is linked to a floating reference rate, for example spot LIBOR. And then it has a principal, nominal or face value f, which we typically set to 1. The floating rate note pays at each time ti, for I is equal to 1 up to n, a coupon which is just the LIBOR spot rate times the time interval. It will also pay the full principal at the terminal time tn. Now we have just seen that a payment of spot LIBOR can be replicated by a portfolio consisting of two bonds, as shown. And thus the value of the floating rate note with face value 1 is simply the sum of these coupon payments, which is given by this sum here, as well as the time little t value of the principal, which is given by this term here. Now this sum here is a telescoping sum where most of the terms cancel out. And thus when we expand this sum and cancel all the terms, we're left with the first term, pt_t0. In particular, on a coupon date, t0, just after the coupon has been paid, a floating rate note trades at par. Now let's consider interest rate swaps. A fixed for floating forward interest rate swap is a contract specified by the following: a number of future dates, little t is the current date, and t0 up to tn are future dates, and the gap ti minus 1 is typically constant, modulo, of course, day count conventions. We also have an agreed fixed rate k and a floating reference rate, which we shall again call LIBOR. And then we have a principal or nominal or face value f, which again we will set to 1. The length of the time interval between successive dates ti, delta, is called the tenor of the swap, and the collection of dates is its tenor structure. Now a swap has two legs. The holder of a payer swap pays at each ti, where I ranges from 1 to n, i.e. not at t0, a fixed rate k times delta, and receives a floating rate L times delta, where L ti minus 1 ti is the LIBOR spot rate at time ti minus 1 for maturity ti. Thus at time ti, the holder of a payer swap has the following cash flow. The other party to the swap owns a receiver swap, and pays a floating rate in return for a fixed rate and would receive the negative of this amount as a payoff. Now the quantity here is precisely the payoff of a forward rate agreement with contract rate K, and as we have seen will therefore have the following value at time little t. It therefore follows that the time t value of the forward payer swap is given by the sum of all of these quantities, i.e. the value of the payer swap is this. The value of the receiver swap is the negative of this. A regular swap is simply a forward swap that starts right now, i.e. has little t equal to t0. Now we've seen that we can regard a forward payer swap as a portfolio of forward rate agreements, all with a common contract rate of K. Equivalently, we can regard a forward payer swap as a portfolio consisting of long a floating rate note, which pays LIBOR, and short a fixed coupon bond with coupon rate equal to K. Recall that the holder of a payer swap is required to pay a rate K, similar to the payment on a coupon bond, and will receive a floating rate, LIBOR, which is equivalent to the payment made by a floating rate note. It therefore follows that the time t value of the swap can also be expressed in the following way. The value of the floating rate note is just the value of this zero coupon bond, and the value of the fixed coupon bond is given as follows. By definition, the forward swap rate S is that value of K which sets the time little t value of the swap equal to 0. Notice that the forward swap rate depends on the current time as well as on the entire tenor structure of the swap. Typically, however, I'll take the entire tenor structure as known and simply refer to the value as S of t, as I do over here, for example. Now, if we express a payer swap as a portfolio of forward rate agreements, then we saw that its value is as follows. Setting this expression equal to 0 and then solving for K, we get the following expression. And hence, this is the forward swap rate. Expressing a payer swap as a portfolio long a floating rate note and short a coupon bond, we obtained the following value for the interest rate swap. Again, setting this equal to 0 and solving for K, we obtain the following. And thus we have expressed the forward swap rate in two ways. Now the first expression on the previous slide for the swap rate shows that the forward swap rate is a weighted average of LIBOR forward rates, i.e. we can express the forward swap rate as follows, where the weights Wi are given by this expression here. As you can see, Wi is simply the value of the TI bond component in a portfolio consisting of these bonds here. The denominator here can be regarded as a security that pays an amount delta J at time Tj. In that sense, it's like an annuity that pays a fixed amount at fixed intervals. As we've said before, the holder of a receiver swap receives fixed and pays floating, i.e. the holder of a receiver swap is simply short a payer swap. Now in practice, the tenor for fixed and floating payments need not be the same. For example, US benchmark swaps pay 3-month LIBOR every 3 months in return for fixed payments every 6 months. In Europe, it's 6-month Euribor floating versus fixed annual. In South Africa, however, the tenor is often 3 months for both fixed and floating payments. Next, we'll consider interest rate options. To begin with, let's have a look at caps and floors. An interest rate cap is an instrument that protects the holder against rising interest rates. It consists of a strip of caplets, where each caplet is a call option on a floating rate. A cap is therefore specified by a tenor structure, T0 less than T1 up to Tn, a floating reference rate, for example LIBOR, against which the holder of the cap seeks protection, a fixed cap rate R, which can be regarded as the strike of each of these caplets, and a notional amount f, which again we set equal to 1. A cap therefore consists of n caplets, and the nth caplet, Cn, has a payoff given by the following expression. At time Tn, it pays of an amount equal to the spot LIBOR rate at time Tn minus 1 minus the cap rate times the time interval delta n, provided that this is non-negative. Else it pays 0. Thus, should the LIBOR spot rate rise above R, the caplet will pay off, and this payoff provides protection against the LIBOR rate rising above the cap rate. Now notice that this payment is made at time Tn. However, the amount that will be paid is already known at time Tn minus 1 because that is the time that we see the LIBOR spot rate. We use this fact to show that each caplet is equivalent to a put option on a zero coupon bond. First, we express the value of the Tn bond at time Tn minus 1 in terms of the LIBOR spot rate, as follows. Then we discount the caplet's payment at time Tn, namely this expression here, by multiplying it by this bond, in other words, by dividing through by this expression. And so the payoff of the caplet at time Tn is equivalent to a payment of this expression here at time Tn minus 1. Now, as an exercise, you will show that this expression here can be rewritten as follows. What we see in the term on the right here is just the value of the Tn bond at time Tn minus 1. We can regard this as a strike, and therefore the expression in brackets here with the plus sign is equivalent to a put option on the Tn bond with maturity Tn minus 1 and strike equal to this ratio here. Moreover, there are 1 plus R times delta n many of these put options. In other words, the nth caplet is equivalent to 1 plus R times delta n many put options on the Tn bond, where the strike of each of these put options is given by this ratio here, and the expiry of the option is Tn minus 1. The payoffs of a cap are therefore equivalent to those of a portfolio of put options on zero coupon bonds. Now, whereas a cap offers protection against rising interest rates, an interest rate floor protects its holder against dropping rates. An interest rate floor can be regarded as a portfolio of put options on a floating reference rate, for example LIBOR. Each such option is then called a floorlet and has the following payoff at time Tn. Some simple mathematics will show that the following parity relationship must hold. A cap minus a floor is equal to a pair swap, where all three instruments have the same tenor structure and fixed rate R. Finally, let's consider swaptions. A swaption is the option to enter a swap contract, say a pair swap, at some future date t, which is the exercise date of the swaption, at a strike rate R. Now, if the tenor structure of the swap is given as follows, where T0 is equal to the exercise date of the swap, then the swaption gives the right, but not the obligation, to receive the following cash flows. This cash flow here, LIBOR minus the strike rate times delta n, will be received at time Tn. Now, these payments look similar to the payments for a cap. However, there's an important difference. Firstly, the cash flows will be negative if the LIBOR rate is less than the strike rate, and for a cap, payments can never be negative. And secondly, once the swaption is exercised, all payments must be made, positive or negative. Now, you could also enter a swap at time capital T at the then prevailing swap rate, ST, and this will lead to the following payments at time Tn. Now recall that the value of a swap entered at the prevailing swap rate has an initial value of 0. So the holder of this swaption could either exercise it, enter the swap, and end up paying a fixed rate of R, or they could enter a swap at the prevailing swap rate and end up paying ST. Clearly, it's preferable to pay R only if R is less than or equal to ST, and thus the holder of the swaption will exercise only if R is less than ST. If R is greater than ST, the swaption will remain unexercised. Now, should the holder of the swaption exercise the swaption, i.e. should R be less than or equal to ST, the holder can also simultaneously enter a receiver swap at the swap rate ST. In that case, the holder will receive L and pay R, and will pay L and receive ST. Note that then the LIBOR payments cancel out. Thus the net payment will be ST minus R, and this will be received at time Tn and only when ST is strictly greater than R. Now the swap rate is already known at time capital T, and so this payment at time Tn can be discounted to time capital T and is therefore equivalent to the following payment at time capital T. It therefore follows that the value of the swaption at its exercise date capital T is given as follows. We've simply summed all of the cash flows at the bottom of the previous slide. Notice again that this sum here can be regarded as the time capital T value of an annuity that pays delta n at time Tn. Now, since a payer swap is equivalent to a floating rate note minus a coupon bond, a payer swaption can be regarded as a put option on a coupon paying bond. Here's why. Suppose that we have the following tenor structure for the underlying swap. Again, assume that the face value is 1 and that the strike rate is R. Let B be a coupon bond, also with coupon rate R and the same tenor structure as the swap. Then the payoff of the swaption is simply the value of the floating rate note at time capital T, the exercise date of the swaption, minus the value of the coupon bond at time capital T, and only if that difference is positive. Since the floating rate note trades at par at the initial date T is equal to T0, the value of the floating rate note is equal to 1. And hence the payoff of the swaption is simply 1 minus BT, provided that this is positive. This looks like the payoff of a put option on a coupon bond with strike equal to 1. And thus a swaption with strike rate R and maturity capital T is equivalent to a put on a coupon paying bond with a coupon rate R, where the strike of the put is equal to 1 and the maturity is capital T. By manipulating this expression over here, you can also show directly that it is equal to this. This is left as an exercise.